With the success of Starship Flight 5, SpaceX accomplished what many believed to be impossible. They successfully caught the Super Heavy booster using the launch tower arms for the first time, and on top of that, Starship landed perfectly in its designated zone in the Indian Ocean, completing a spectacular suborbital mission. Without wasting any time after the triumph of Flight 5, SpaceX has already started preparing for the next test mission, Flight 6. Let's take a look at the key events from the past week at Starbase. Following the return of Booster 12 to the build site after Flight 5, teams began working diligently to repair minor damage to the launch pad infrastructure. These repairs primarily focused on the launch mount, launch tower, and chopsticks, ensuring everything was in order for the upcoming Flight 6 test campaign. After Flight 4 in June, SpaceX needed a full month to repair the launch site and prepare for Booster 12's static fire tests. However, since the damage from Flight 5 was much less severe, SpaceX required less time to prepare the site for Flight 6 pre-launch activities. Once the launch pad was deemed ready for Starship testing again, Booster 13, which will be launched in the 6th integrated flight test, was rolled out from the megabay and transported to the launch site. The design of Booster 13 closely mirrors its predecessor, Booster 12, with only a few visible changes. One notable change is the removal of the methane vents at the top of the booster. Additionally, the cowbell-shaped oxygen vents outside the common dome area have been redesigned. These vents also serve as reaction control system thrusters, helping to stabilize the booster during its return to the launch pad. A significant modification to Booster 13 is the addition of new black-painted stringers over the alignment pin sockets and the existing forward dome stringers. First seen on Booster 12, these stringers help prevent the alignment sockets and dome stringers from snagging or tearing against the landing rail bumper pads. This engineering upgrade improves the safety and reliability of the booster catch operations. After Booster 13 arrived at the launch site, it was moved towards the launch pad, placed in between the chopsticks, and carefully lifted and placed onto the launch mount. The process went smoothly, confirming that the tower arms were not compromised by the forces experienced during the catch attempt with Booster 12. Once the booster was securely placed on the OLM, the teams began preparing for static fire testing. Wednesday night, they carried out thrust vector control tests by gimbaling the engines, performed an ambient pressure test on the booster, and tested the launch mount's detonation suppression system in preparation for the static fire attempt. Booster 13's static fire test was conducted on Thursday, October 24th. During the test, all 33 Raptor engines ignited and fired for a full 8 seconds before shutting down. Static fire tests like this are crucial for verifying that the booster's plumbing, valves, ignition systems, and engines are functioning properly before it proceeds to an actual launch. With the static fire testing now complete, Booster 13 will soon be returned to the build site for system checks and further processing in preparation for Flight 6. Engineers will make adjustments to the booster's design and update its software based on the data from Booster 12 return and landing during Flight 5. Meanwhile, Starship 31, which will fly alongside Booster 13, is currently in the high bay undergoing heat tile replacements. Teams have nearly finished swapping out the old tiles with new and improved ones. These upgraded tiles are designed to ensure a smooth re-entry and ocean splashdown for Ship 31, similar to Ship 30. Future flights will further improve the heat tiles using data collected from both Flight 5 and upcoming missions. SpaceX is also expected to install heat tiles wrapped in aluminium on Ship 31 just like they did on Ship 30. This test will provide valuable insights into how stainless steel, the primary material used in Starship construction, behaves under extreme re-entry conditions. Aluminium begins to melt at approximately 660 degrees Celsius, which is close to the temperature at which stainless steel begins to lose its strength. By wrapping heat tiles in aluminium, engineers can simulate how the stainless steel structure of Starship might respond if it is exposed to re-entry heat, such as when tiles are lost mid-flight. This data will help SpaceX better understand the thermal limits of stainless steel and improve the design and safety of future Starship missions. Now that Booster 13 has completed its pre-launch testing, and work on Ship 31 is nearing completion, it's evident that SpaceX is almost ready for the Flight 6 launch. The only major test remaining is the full-stack wet dress rehearsal, which typically occurs a week or two before launch. SpaceX currently holds a license to launch 5 Starships per year, provided they adhere to the Flight 5 mission profile, and do not introduce any significant changes to the vehicles. Moreover, the FAA has confirmed that all events in Flight 5 were within the scope of authorized activities, and no investigation is needed. This means that SpaceX already has FAA approval for Flight 6, assuming it follows the same flight plan as Flight 5. Given the current pace of work at Starbase and the FAA approval already in place, Flight 6 is expected to take place between mid and late November, assuming everything proceeds smoothly. What's your prediction for when SpaceX will launch the next Starship and attempt another booster catch? Share your thoughts in the comments below. In parallel with preparations for Flight 6, teams are also progressing steadily with the construction of Pad B. The flame trench construction is advancing smoothly, with rebar placement underway for the trench walls, while excavation continues to shape the trench. Once completed, the flame trench will be equipped with a water deluge system, similar to the one SpaceX uses for Falcon rocket launches. By releasing large volumes of water onto the launch pad just before ignition, the system helps to absorb the intense heat and reduce the deafening noise produced during a Starship launch. This system offers a significant improvement over the current water-cooled steel plates by providing more uniform cooling and better sound suppression, which reduces the stress on both the launch pad and the rocket itself. A cable tray belt and 2 heat exchangers were delivered to the launch site this past week for integration with Pad B. The cable tray belt was installed on the Pad B launch tower on October 20th. It will serve as a critical support structure, housing and organizing all the electrical and hydraulic cables, along with other hoses and attachments that run from the tower to the launch arm carriage. The next major step in construction is the installation of the launch tower arms and the carriage assembly. They are currently being prepared at the Sanchez site for transportation to the launch pad. The launch mount for Pad B is also under construction at Sanchez. Teams are actively welding the individual sections of the launch mount. As for the heat exchangers that were delivered, they were installed at the tank farm Monday afternoon. They play a crucial role in supercooling the propellants before they are loaded into the launch vehicle. In the coming days, more heat exchangers and propellant storage tanks are expected to arrive as SpaceX expands the existing tank farm to meet the operational needs of Pad B. At the build site, teams are continuing to stack Starship 34 inside Megabay 2. The ship's common dome was recently moved into the facility and stacked with previously assembled sections. In an unexpected development, on October 22nd, SpaceX recovered the Booster 12 hot stage ring from the ocean. This ring was jettisoned after stage separation during Flight 5 to reduce weight and save fuel for the booster's return. The recovered ring, mostly intact, provides SpaceX with valuable data on the structural integrity of the ring after exposure to high temperatures and dynamic forces during stage separation and re-entry. SpaceX plans to develop an integrated lightweight hot stage ring for future boosters, which won't need to be jettisoned. This would enable full booster reusability, unlike the current design, where discarding the ring limits recovery of the complete booster. On October 23rd, SpaceX achieved a significant milestone by conducting back-to-back testing of a Raptor engine at their McGregor test facility. Reports suggest they completed 39 tests, with 34 of those occurring within just 10 minutes. The duration of each test ranged between 5 and 15 seconds, with most lasting around 8 seconds. Similar short-duration back-to-back tests were conducted on October 24th too. This unprecedented series of tests likely involved the Raptor V3 engine. While the specific motivations for testing remain unclear, the rapid testing likely aims to assess the engine's restart capabilities, which are crucial for missions requiring multiple ignitions, such as landings and in-orbit maneuvers. Also, by testing the engine in quick succession, the team gathers extensive data, enabling them to refine the Raptor design more efficiently. Additionally, these tests may act as a stress test, assessing how the engine performs under sustained operation and identifying any potential design flaws or weaknesses. The tests could also be simulating engine failure scenarios, focusing on quick detection and restart after a fault. Furthermore, by systematically adjusting parameters like fuel flow rate or ignition timing, SpaceX can fine-tune the engine's efficiency, stability, and reliability based on the collected performance data. As SpaceX continues to push the boundaries of space technology, these tests are essential steps toward achieving their ambitious goals in the space industry. Now, let's discuss the latest updates from the world of science and technology. SpaceX recently marked a significant milestone by completing its 100th orbital launch of the year. This mission took place on October 19th from Vandenberg Space Force Base in California, where a Falcon 9 rocket carried the final batch of 20 OneWeb Internet satellites into space. After stage separation, the rocket's first stage executed a precise re-entry and successfully landed at Vandenberg's Landing Zone 4, marking the 7th landing for this particular booster, and the 357th successful recovery for SpaceX overall. Meanwhile, the Falcon 9's upper stage continued its journey, delivering the satellites to their designated low Earth orbit, where they were deployed in batches. Over the following weeks, the satellites will utilize their onboard thrusters to raise their altitudes, ultimately settling into a 1,200 kilometers orbit inclined at 86.4 degrees to the equator. OneWeb's mission is to provide global broadband internet service through its satellite constellation. The recent launch comprised the final batch of its first-generation constellation, initially planned to consist of 648 satellites, including 60 spares. With a total of 654 satellites now in orbit, OneWeb has more than enough capacity to offer global coverage. Although OneWeb has commenced commercial services, complete global coverage remains elusive due to delays in installing all necessary ground stations. To date, only 38 of the planned 45 ground stations, known as gateways, have been installed. These gateways are essential for connecting the satellite network to users on the ground. Historically, OneWeb relied on Russian Soyuz rockets to deploy the majority of its Gen 1 satellites. However, after Russia's invasion of Ukraine in 2022, this arrangement came to an abrupt halt, forcing OneWeb to find alternative launch providers. In a somewhat surprising move, SpaceX stepped in to assist OneWeb, despite the two companies being direct competitors in the satellite broadband market. This partnership began in March 2022, and SpaceX has since been instrumental in helping OneWeb complete its satellite constellation. Looking ahead, OneWeb plans to launch its second-generation satellites in the coming years, which will further enhance network capacity and provide greater flexibility for users. Blue Origin successfully launched its new Shepard NS-27 mission on October 23, marking a significant milestone in the company's suborbital flight program. The flight was uncrewed and aimed to validate the capabilities of the latest New Shepard rocket capsule combination. The mission introduced the second human-rated New Shepard vehicle, which includes a first stage known as Booster NS-5 and the crew capsule named RSS Kármán Line. The rocket carried a total of 12 research payloads, with 5 positioned on the booster and 7 housed inside the capsule. Approximately 2 minutes and 40 seconds after liftoff, the rocket's first stage separated from the second stage and began its descent back to Earth. Less than 7.5 minutes into the flight, the booster executed a powered touchdown at landing zone, located 3.2 kilometers north of the launch pad. Meanwhile, the crew capsule ascended to an altitude of 100 kilometers above sea level, commonly recognized as the boundary of space, before returning to Earth for a parachute-assisted landing. This latest New Shepard vehicle features technology upgrades designed to enhance performance and reusability, an updated livery, and improved accommodations for payloads on the booster. The data gathered from this test flight will be crucial in determining whether the vehicle is ready to carry humans into space. Thank you for tuning in for the latest science news and Starship updates. If you enjoyed this video, please hit the like button, leave a comment, and share it with your friends. Also, don't forget to subscribe to the channel and turn on notifications so you never miss an episode.